In the following examples, we are given some complex numbers. The first three are in rectangular form, and the last one is in polar or trigonometric form. And what we're going to do is we're going to find the powers that we're being asked to find. Okay, so find the given power, and then they want us to write our answer in rectangular form. So I'm going to tell you of the four problems that we see right here. The first three are going to be a little bit more involved. The last one is actually the easier of the four. So what we're going to do is we'll take a look first at problem number 1. Again, it's a little bit more involved, but that's okay. We're going to say 1 minus I to the 10th power. Now, in order to figure this out, we first need to convert it to polar form. So we need to get it to look something like this, R cis. Okay, so we need to convert it to polar form so that then we can apply de Moivre's theorem. And in applying de Moivre's theorem, it's actually a very simple process, which is a very simple formula written there in compact form. Okay, so first things first, let's convert from rectangular to polar form. So we have x equal to 1 and y equal to -1, because that's the coefficient here of the minus I. All right, now we can find the r value, which is going to be 1 square plus a -1 square, which is really just going to be the square root of 2. So our r value is going to be the square root of 2. And let me write that down in a different color. R equal the square root of 2. Okay, so now we're going to find the tangent of theta. And we know that the tangent of theta from this formula down here is y divided by x. So in this case, -1 divided by 1, which is just -1. Okay, now the one thing that I forgot to mention, and let's go ahead and take a look at it now, is what quadrant are we dealing with? Well, we have a positive x but a negative y. Okay, a positive x but a negative y. That means that our polar graph might look something like this. Okay, the vector anyway, and we'd have an angle that we would rotate about counterclockwise, and it's going to be somewhere in the neighborhood of 270 degrees to 360 degrees. So we know that we're dealing with quadrant 4. So we're going to find a value of theta in quadrant 4. We just have to figure out, well, where is tangent -1 in quadrant 4? But that's not terribly difficult to figure out. So let's go ahead and take a look at our unit circle. So here's our unit circle. We're going to zoom in on quadrant 4. Now we're looking for where tangent of theta equals -1. And tangent, recall, is y divided by x. That means that y and x have to be the same but opposite in sign. And so we actually find that right here at 315 degrees, 7 pi over 4 radians. And there are the coordinates x and y, cosine and sine. Cosine and sine. Okay, so we're going to utilize that next. Okay, well, actually, right now, I think we just need the degree evaluation. Okay, so we just need the degree evaluation. So we're good. We've got 315 degrees. So let's take it back to our problem. Right over here. Okay, so we know that theta equals 315 degrees, and that's consistent with what we figured, that it was going to be between 270 and 360 degrees. Okay, so next thing we're going to do is we're going to write this out in R cis notation, and then we're going to raise it to the 10th power. So let's see here. We're going to have something that looks like this, R cis theta to the 10th power. Okay, so let's see what we've got. We've got the square root of 2, right? And then cis 315 to the 10th power. Looks something like that. Now, you have to kind of remember something. The square root of 2 is also 2 to the 1/2 power. So that's going to come in handy right now because we're going to need to know that. Okay, so let's consider that this is 2 to the 1/2 power raised to the 10th power, because now we're going back and we're looking at de Moivre's theorem here, which is this that I'm about to highlight for you. Oops, that wasn't the highlighter. This right here. Okay, so that to the 10th power, and then cis, the cosine imaginary sine, of 10 times 315 degrees. Okay, so it looks like that. We end up with 2 to the 5th power, cis of 3150, if you do that on your calculator, unless you can do it in your head. All right, so that's not terribly difficult. Okay, that's not terribly difficult. Then what we need to do is, if you recall, you'd want to find a coterminal angle, suppose 3150, and you're going to subtract 360, but how many times? Well, in this case, the smallest positive coterminal, you'd have to subtract 368 times to get 270 degrees. Okay, so what we're going to find is that we are actually working with 2 to the 5th power, which is 32, cis of 270. Okay, 32 cis of 270. So that's not terribly difficult, because now all we have to do is figure out, well, what is the cosine of 270 and what is the imaginary sine of 270. All right, not terribly difficult at all. So let's go ahead and look for the cosine and sine of 270. So let's look at our circle one more time. Zoom in here, and we've got it. It's this right here. The cosine is 0 and the sine is -1, and this is actually going to make our problem really nice and simple. So let's take a look. Okay, right here. So then we have 32 times cosine 270 was 0 plus I, and the sine of 270 was -1. So we end up with -32i, because this becomes -i. All right, this right here is -i times 32, -32i. And so this right here is our answer for 1 minus I to the 10th power. It ends up being -32i. So really neat example here. Again, an application of de Moivre's theorem. We're going to take a look at a few more examples. So if you're done, if you think you know what to do, I mean, this may be a good time to exit, but I think you probably need to fast forward at least to see how to apply problem number 4. But problem number 4 is actually very similar to what we did in this step right here. Okay, so it might be a good time to pause and maybe advance. Otherwise, give me a second and I'm going to clear the screen. Okay, so here's yet again another example, and let's consider this one right here. Let's first start talking about what quadrant we're dealing with. We have an x is negative and a y is positive. So we're somewhere in this ballpark, and we're going to consider that the angle is somewhere between 90 and 180 degrees. So that's what we're dealing with here, something between 90 and 180 degrees. And so we are in quadrant 2. All right, we're dealing with quadrant 2. Okay, so let's find our r value. R will equal the square root of a negative square root of 3 square plus 1 square. Okay, that works out to be a 3 plus 1, which is the square root of 4, which is 2. So I'm going to write that in a different color. Let's write r equals 2. We're going to come back to that in just a second. And then let's find our tangent value. Tangent again being y divided by x. And in this case, that's going to be 1 divided by a negative square root of 3. Okay, so we're going to flip over to our unit circle and we're going to figure that out. All right, looking at our unit circle here, I'm just going to cut to the chase. We're looking for 150. The proof is that 1/2 divided by negative square root of 3 over 2 is really 1/2 times 2 over the negative square root of 3, leaving you with 1 over negative square root of 3, which is what we were looking for. So we really don't care about this right now. What we do care about is the 150 degrees. That's our theta that we're going to be working with. Okay, so let's take a look here. We've got theta equal to 150 degrees. All right, we can work with that. Now let's write it in R-cis form. 2 cosine imaginary sine, the cis of 150, all raised to the 6th power. So this is going to look like this, 2 to the 6th power, because this is what, again, Moivre's theorem says right here. And then cosine imaginary sine of 6 times 150. And so we're going to get 2 to the 6th power, which is 64. And then the cosine imaginary sine, 6 times 150, ends up being 900. And now again, we've got to find a coterminal angle. 900 minus the smallest positive coterminal would be 2 rotations of 360. And that will give us 180 degrees. And so this one we know is going to work out nicely, because 180 is one of those things on the unit circle that's real easy to figure out. But don't worry, we'll still look at the unit circle, not to worry. So we're going to have 64 cis of 180. All right, so what does that look like? 64, and then we're going to put here the cosine plus the imaginary sine, and then we'll distribute and we'll figure that out. So let's take a look at 180 real quick here on the circle. The cosine is -1, the sine is 0. All right, let's fill that in over here. So the cosine value goes right in here, -1, and then the sine is 0. So we end up with something that looks like -64, because this is 0. So we just have to multiply that times that. We get -64. And that is what negative square root of 3 plus I to the 6th power is. So not really that difficult. Okay, not really that difficult. All right, so I'm going to pause here in just a second, but let me tell you, I'm thinking about it, and I think I'm going to leave this one right here as an exercise, and we will just jump to problem number 4. All right, so give me a second to clear the screen. Okay, so we are jumping straight into problem number 4, and this one is set up nicely. It's already in polar form, and so we can go straight in and apply de Moivre's theorem. All right, so let's take a look here. What is this going to look like? It's going to look like 3 to the 4th power cosine imaginary sine of 4 times 15, something like that. So 3 to the 4th power, not a big deal. You can do it on your calculator if you're really good. You can do it in your head. 3 to the 4th power is 81. And then that's going to pull out for us the cosine imaginary sine of 60. And if you're really good, you probably have that memorized from the unit circle. All right, so let's see here. 81 times the cosine of 60 plus the imaginary sine of 60. And let's go ahead and look at the unit circle and figure that out real quickly. 60 degrees, here is the cosine, here is the sine. Cosine is 1/2, and the sine is the square root of 3 over 2. We're going to zoom out. We're going to go back. We're going to zoom in right over here for you. And we're going to fill in what it is that we know. We know this is 1/2. And we know this is the square root of 3 over 2. And now all we have to do is distribute, just like that. We're going to end up with 81 over 2 plus 81 square root of 3 over 2 times the imaginary unit I. And that's what we're left with because we can't reduce any of this. All right, so these are 3 really great examples of how to apply de Moivre's theorem to find powers of complex numbers, to find powers of trigonometric or polar formed numbers as well. All right, so a little introduction to the theorem. It's a really neat theorem. It's very easy to apply. There's quite a bit going on here, especially if you start off in rectangular form, but hopefully otherwise this helped you out. Kind of a long-winded video. We did cut it short a little bit. So if the video was helpful, be sure to like and subscribe.